Hello everyone. So the next section is going to be 6.2, the definite integral. And I know in the previous section we started doing, Riemann sums and pretty much estimating what an integral is with like rectangles and trapezoids and all that. In this section, we're going to start getting into the more specifics of finding the actual area between the curve or the function and the x-axis. And you're going to notice a few things that are a little bit different here, but this is going to be a good introduction to what we're eventually going to do with integration rules and techniques, kind of like how we used to have derivative rules and techniques. Integration has their own set of rules as well. So let's get into finding the area, and I'm going to start phrasing it like this: finding the area between the curve and the x-axis. Okay, because sometimes it's not always underneath the curve. In a case like this, where you have like this portion of the function, you're going to have an area above the curve. All right, and in cases like this, you're going to have to treat it a little bit differently. So let's just kind of get into that. All right, so obviously these are shapes that we can easily find the area of. So if I were to find the area of this semicircle, well, we know the area of a full circle is pi r squared. So a semicircle would be 1/2 pi r squared. So it's 1/2 pi. Our radius here is 2, so it's 2 squared. So this area is equal to 4 pi divided by 2, so 2 pi. Okay, and something I'm going to make note of here is that this is an area that's above the x-axis. All right, so I'm going to write that. So above x-axis. Okay. All right, so if I look at this area of this shape right here, well, this is going to be a trapezoid, and hopefully you remember from the last section what the area of a trapezoid is. It's 1/2 times base 1, which is a length of 4, plus base 2, which is a length of 1, and then times the height of 2. All right, well, I know the 2 and the 1/2 will pretty much cancel each other out, and then multiply that by 5, we get 5. And again, I'm also going to note that this is an area above the x-axis. All right. And finally, this triangle right here, area of the triangle is 1/2 base times height. So 1/2 times base length of 4, a height of 2. Right? So the 2 and 1/2 cancel out again, and we have 4. And this area of this triangle is going to be below the x-axis. Now, why is this important to know whether it's above or below? Well, that's just going to determine whether that area is negative or positive. So here and this is what the notation of the integral is saying. This integral is saying what is the area underneath the curve for the function between the intervals 0 to 4. So from 0 to 4, that area is 2 pi. From 4 to 8, that area is 5. From 8 to 12, that area, since it's below the x-axis, we're going to say that that's -4. So any areas below the x-axis are negative. And then over here, if I wanted to know, I'll start with this one, from 0 to 8, right? The area from 0 to 8, well, I'm going to go ahead and just add those two areas up. So it's going to be 2 pi plus 5. And then from 0 to 12, again, I have to add all of those areas, but I'm going to subtract that area below the x-axis. So that's equal to 2 pi plus 5 minus 4, which is equal to 2 pi plus 1. All right, so this is just kind of, you're never going to see easy examples like this where you can find the area, but this is a good introduction to what we're eventually going to be working towards. And again, my goal is to kind of build you up with like all of these simple concepts so that we can eventually get into the heavy stuff, especially later when we get to revolutions. All right. Now, if we look at this, it's to set up the integral for the following. So again, when in a case like this, we have our function, and we're looking to see like where are they trying to find the area from. So really the bounds, and this is going to help us kind of establish what the bounds of our integral is going to be. So if you notice, they're trying to find the area, like they have a shaded region from -2 up to here, and another shaded region from there. Right, but whenever you take the integral of something, you're taking into account like all of the negative areas and the positive areas. So really, it's just a matter of setting up your integral from your lower bound 2. The lower bound is always on the bottom, and your upper bound 3. Well, it's not always on the bottom, but it's by convention we put it on the bottom. Sorry, -2. whatever, I already messed up. I'm not going to re-record this. All right, so then it's going to be from -2 to 3 of the function 1/9 x cubed. And what we're essentially going to do is we're always going to take that, or take the integral with respect to dx, okay? And as far as what dx actually is, I guess just to quickly go over it, like before when we were doing Riemann sums, we were taking like rectangle, little rectangles all the way through. And I emphasized this a little bit on the last video, but the smaller the rectangles, the more accurate your area under the curve is going to be. And really this dx is essentially representing an infinitesimally small rectangle width so that we can get the most accurate area underneath that curve. So that's essentially what the dx represents. So over here, when I'm going, when I take the integral of this, again, it's just going to be this. This is the function, so it's the integral of the function 3/4 x squared minus 2x minus 1 dx, right? And it's going, and they're basically integrating from -1 to 4. All right, pretty simple. Okay, so the next thing we're going to do is sketch this function and give a graphical representation of what this integral is trying to ask for. So we know that this function is 4 minus x squared, and if I were to graph that, that's a parabola facing down with the y-intercept at 4. If I plug in 1 and -1, I'll have 3. If I plug in -2, I'll get 0. And -3 and +3 is -5. All right. I mean, of course you can, and that's awful, but whatever, that's fine. And you can do this on your graphing calculator, of course, if you want to kind of look to see what the sketch looks like. And that's kind of my poorly drawn parabola, but that's fine. So essentially what we want to do here is we want to know what, integrate this from -2 to 1. So the area that we're interested in is like starting here at -2 and going up to 1. So this is the area that we are interested in finding. All right, we're not interested in that. We're only interested in the area between -2 to 1. At least this integral is. All right, so if I look at this graph, God, I feel like I'm back in algebra just graphing these functions. I hated graphing. It's something like that, shifted to the right one here. I remember it goes up in 1 like that, and then if I put in, let's see, if I put in 5, I get 2. So there we go. Kind of the best I can do. So we want to know what the area of this is between 2 and 3. So 2 is there, 3 is there. So this is the area underneath the curve that I'm interested in. All right, from the curve to the x-axis. All right, and then this is that's a linear function. So we're does y-intercept at -1, slope of 1 over 3, 1 over 3, down 1 over 3. And see how straight I can. That was horrible. Okay, well that's fine. We'll survive. All right. And then we want to know the area from -2 up until 4. So really we're interested in knowing this negative area here and this tiny little sliver of a positive area. All right. And what I want you guys to do is also use the calculator to evaluate this. All right. So as far as the calculator function is concerned, I did go over this in the last video, but I'll review it again here. If you go to math, and then you go down, I don't remember the number, and again, I am recording this without my graphing calculator. I'm going to see if I can maybe pause the video for a second, have it, and then transition to me giving you the answers after plugging it into the computer. But you're gonna look for the function fn int, right, which is basically the integration function, and then you're gonna put in each of your function, your f of x, with respect to x, and your lower bound. I'm going to put lower bound and upper bound of your integral. All right. So try practicing using your calculator. I'm going to go figure these out and come back in just a second. And voila, there are the answers if you plug them in your calculator. If you don't get that, then that's fine. All right. So that was quick. Now let me find the next page. I should have been ready. Here we go. Okay, so now as far as some properties of definite or just integrals in general, these are definitely some rules that I want you to keep in mind as you do integral techniques, especially this one of the constant. this is just kind of like, similar to when we did like properties of limits. It's a lot of times half of the battle in calculus is manipulating your integrals or your function or whatever problem you're working with, manipulating the problem to where it's easier to apply the calculus rules that you know. It requires good use of good knowledge of algebra, which I know is a lot of people's weak area, but that's fine. So the first property of integration that we're going to talk about is the zero integral. Essentially, this is telling you that if you're integrating from let's call it a bound A, and you're also integrating from that same bound, well, I mean, that's like you're almost calculating the area of a rectangle with the width of 0, pretty much, right? So if they ever ask you to integrate from one bound and it's the same bound, and well, the lower and upper limit of the upper bound of the integral is the same, then the integral is just equal to 0. Very straightforward. All right. One that I don't see too often, but I see every now and then, is if you have the integral from, let's say, from b to a, right, of f of x dx. All right, then you can essentially, change your bounds, right? You can go from a to b instead of f of x dx. But if you do switch your bounds around, then this is then you're basically negating what the original is. So it's going to be negative instead. So just make sure you remember that. This is the one that I see the most, or the one that I know is going to be the most helpful, especially when we do like U substitution, integration by parts, partial fraction decomposition. When you multiply a function by a constant, let's say you have the integral from a to b of k times f of x dx. If your entire function is being multiplied by a constant, one thing you can do is you can get that constant and move it outside of the integral and then integrate the function easier. So this is the same thing as saying k integral from a to b of f of x dx. This is one that we are going to do a lot. Decomposition, I've seen this whenever with graphical problems, but it's worth noting. If you have an integral from a to b of f of x dx, and you know that there is a value c in between this integral, you can break up the integral into parts. You can instead do the integral from a to c, knowing that c is between a and b, of f of x dx. And then add from c to b. So you're taking the integral from a to c and then from c to b just separately. And that works too. From c to b of f of x dx. The addition rule, this can be helpful. It's not always necessary, but I've seen problems where it's just much easier to break apart your integral into pieces and look at each one separately. But if I have the integral from a to b of two functions added to each other, let's just say f of x plus g of x dx, then you can actually break that apart and take the integral of each one separately. So the integral from a to b of f of x dx plus the integral of a to b, same bounds, of g of x dx. All right, and same thing for subtraction, except instead of addition, subtraction. So from a to b of f of x minus g of x dx is equal to the integral from a to b of f of x dx minus integral of a to b g of x dx. Okay. And this is just kind of like some basic problems to kind of that apply those rules. So let's just kind of get through them fairly quickly. I don't want this video to be too long. So even though probably is already. But anyways, find the following if possible. So again, like I said, if they wanted you to find the integral from 5 to 1, first of all, that's silly. Usually you want your lower, your smaller number to be your lower bound, but that's fine. You can rewrite this as the integral from 1 to 5 of f of x dx, but you're going to take the negative version of that. All right, and seeing how we're only given these three integrals, or the answers to these three integrals, from negative 2 to 1 is 4, from 1 to 5 is negative 3, and from negative 2 to 1 of g of x is 8, right? Now we know that this integral, which is from 1 to 5, is negative 3, so this is equal to negative 3, which is positive 3. From here, we have the integral from negative 2 to 5. Well, I don't have any bounds from -2 to 5, but I do have it broken up into little pieces. I have from -2 to 1 and then from 1 to 5. So essentially, I can just go ahead, I can think of this as these two added together, right? So if I know that 1 is in between -2 and 5, I can go ahead and find the integral from -2 to 1, which is 4, and then add that with the integral from 1 to 5, and that's -3. So that's equal to 1. All right, similar over here. Well, not similar, but like if you here we can go ahead and use our addition rule and then that constant, which I really want us to get good at. So I can break this up instead as the integral from -2 to 1 of f of x plus, and then I can take the constant outside the integral. So 2 times the integral of -2 to 1 of g of x, right? So this we know was 4 plus 2 times, and then we know that the one from g of x is 8. So that's 4 plus 16 is 20. All right. Here we want to know the integral from 0 to 1. Well, I don't have one. So that's just not possible. All right, not possible with the information given. I don't have any information about what the area is from 0 specifically to any other bound. So with the information given. And then if I look at this one, the integral from 1 to -2 of 3 of f of x, well, again, I can take out the 3, right? And I know when it comes to the integral of f of x, I don't necessarily have any with 1 to -2, but I do have from 2 to -1. So I can, reverse my bounds to be -2 and 1 of f of x dx. But remember, if I reversed it, I got to negate whatever my answer is for that. So it's going to be -3 times +4, so that's -12. And then lastly, we have this one. Sure, you can go ahead and break this up, but I already recognize that they're asking me to find the bounds from 5 to itself, and that's just going to be 0. All right, so hopefully that was simple enough. Whenever we do the intro to any new concept, it's always going to be a quick video and a simple one. So hopefully that was easy and you guys understand what's going on. And the next section will be integration techniques, and that's going to be one where you're going to just have to drill and kill a whole bunch of them until you get it. So similar to like the basic differentiation techniques with power rule and all that. So I'll let you guys go. If you have any questions, make sure you ask and get started on the problem set. Take care.